For generations, our devices have been tethered by a fundamental limitation: the finite lifespan of their power source. We live in an era of constant recharging, a cycle dictated by the chemical reactions within our batteries. But what if this paradigm could be shattered? What if a power source could last not just days or years, but millennia? According to materials scientists and physicists, a revolutionary technology is emerging from the most unlikely of places: nuclear waste. This is the promise of the 28,000-year battery, a concept once confined to science fiction, now on the cusp of reality. Today, our world runs on lithium-ion batteries. From the smartphone in your pocket to the electric vehicle on the road, these power cells are ubiquitous. Yet, they come with significant drawbacks: limited lifespan, a reliance on rare earth minerals, and environmental concerns associated with both extraction and disposal. Experts in energy research have long sought viable alternatives, a quest driven by the need for greater efficiency, longevity, and sustainability. The search for a truly independent, enduring power source has intensified, pointing towards a radical departure from conventional chemistry. Enter a concept that sounds almost alchemical: turning nuclear waste into a clean, continuous energy source. This isn't theoretical physics from a century ago, it's the contemporary vision of betavoltaic nuclear batteries. At its core, this technology proposes harvesting energy from radioactive isotopes, specifically carbon-14, encased within artificial diamonds. Researchers at institutions like the University of Bristol have been at the forefront of demonstrating this potential, suggesting a future where power isn't drawn from chemical reactions, but from the slow, steady decay of atomic nuclei, safely contained within one of the hardest known materials. The journey into nuclear diamond technology gained significant momentum through the pioneering efforts of the University of Bristol's Cabot Institute. In 2016, their team announced a significant breakthrough: they had successfully demonstrated a prototype diamond battery capable of generating a small electrical current from a radioactive source. This wasn't merely a theoretical exercise, it was a tangible proof of concept. As Dr. Tom Scott, a lead researcher, stated, their work illustrated the potential to turn a global problem, nuclear waste, into a long-term power solution, a truly transformative application of materials science. To grasp this technology, we must first understand betavoltaics. This is a form of nuclear battery that harnesses the energy of beta decay. Unlike traditional nuclear power plants that generate heat to drive turbines, betavoltaic devices directly convert the kinetic energy of emitted beta particles, which are high-speed electrons, into electrical current. This direct conversion process is inherently more efficient for low-power, long-duration applications. According to nuclear engineers, it sidesteps the thermal inefficiencies of larger reactors, offering a pathway to miniature, self-contained power sources without moving parts or external heat requirements. Beta decay is a type of radioactive decay in which a beta particle, an electron or a positron, is emitted from an atomic nucleus. In the context of these batteries, we're primarily concerned with beta- decay, where a neutron in the nucleus transforms into a proton, emitting an electron and an antineutrino. This emitted electron, or beta particle, carries kinetic energy. When this high-speed electron passes through a semiconductor material, it excites other electrons within that material, creating an electric current. Nuclear physicists explain this process as a continuous, predictable release of energy, fundamental to the battery's operation. The choice of radioactive source is critical, and for the diamond battery, carbon-14 is the star. Carbon-14 is a weakly radioactive isotope of carbon, famed for its use in radiocarbon dating. What makes it ideal for betavoltaics? Its relatively long half-life of 5,730 years means it decays slowly, providing a consistent, low-power output for an extremely extended period. Furthermore, its beta particles are low energy, making them easier to shield and less hazardous than higher energy emitters. As nuclear chemists note, its properties are uniquely suited to the long-duration, low-power requirements of this technology. One of the most compelling aspects of this technology is its potential to address a persistent environmental challenge: nuclear waste. Carbon-14 is a byproduct of graphite-moderated nuclear reactors, specifically generated when neutrons interact with the nitrogen impurities within the graphite used as a moderator. Instead of simply storing this long-lived radioactive waste, the nuclear diamond battery proposes to repurpose it. According to proponents, this waste-to-wealth approach transforms a hazardous material into a valuable energy asset, offering a compelling argument for its development and deployment. The diamond in nuclear diamond tech is more than just a casing, it's an integral part of the energy conversion process. Lab-grown diamonds, synthesized through processes like chemical vapor deposition, CVD, are exceptional semiconductors. When carbon-14 is incorporated directly into the diamond's lattice structure, the emitted beta particles interact within the diamond itself. The diamond acts as both the radioactive source and the semiconductor transducer. Materials scientists explain that diamond's wide bandgap and extreme hardness make it uniquely efficient at converting beta particle energy into electrical current, while also providing inherent radiation shielding. The most striking feature of these batteries is their projected lifespan. Due to the long half-life of carbon-14, these diamond cells are theoretically capable of generating continuous electricity for thousands of years without ever needing to be recharged. Imagine a device that powers itself for 28,000 years, a duration that stretches far beyond human recorded history. This longevity is not merely an extended battery life, it's a fundamental redefinition of power permanence. Energy experts underscore that such a capability opens up entirely new possibilities for applications that demand extreme durability and autonomy, free from human intervention. The long-term vision for nuclear diamond batteries is nothing short of revolutionary, to eliminate the need for traditional lithium-ion batteries in a wide array of applications. Consider the impact: no more planned obsolescence due to battery degradation, no more disposal of toxic chemical cells, and a significantly reduced environmental footprint. Energy policy analysts suggest that while they won't power a car directly in the same way, their capacity for persistent, low-power output could redefine entire product categories. This shift could usher in an era where power is no longer a consumable, but an integrated, virtually eternal component of our technology. While the concept is powerful, transforming it into a practical device involves significant engineering hurdles. One of the primary challenges is miniaturization. To power a smartphone, for instance, the battery needs to be compact, yet still provide sufficient power output. The current prototypes generate very small currents. Scaling this up while keeping the device small enough for consumer electronics requires incredibly efficient energy conversion and a high concentration of the carbon-14 isotope within the diamond. Device engineers emphasize that achieving this balance between power density and minuscule form factor is an ongoing area of intensive research and development. Another critical engineering challenge lies in radiation shielding. While carbon-14 emits relatively low-energy beta particles, safety is paramount. The diamond itself provides excellent inherent shielding, absorbing most of the radiation internally. However, for practical applications, especially those used close to humans, additional, ultra-thin layers of non-radioactive diamond are typically added. Radiation safety experts stress that any external radiation must be negligible, less than background radiation. The design must ensure that the radioactive material is completely contained, posing no risk to users, even if the device is damaged. Public acceptance of nuclear technology, even in this benign form, hinges on rigorous safety. Developers of nuclear diamond batteries are working closely with regulatory bodies to establish comprehensive safety protocols. According to published research, the beta particles from carbon-14 are absorbed by just a few millimeters of solid material, including the diamond casing itself. This means that, unlike more powerful isotopes, the radiation hazard is confined internally. Engineers confirm that the finished batteries are designed to be completely inert externally, emitting no measurable radiation, making them safe for consumer use in medical applications. Imagine a smartphone that never needs to be charged. The implications for daily life are profound. No more low battery anxiety, no more searching for outlets, and a complete liberation from charging cables. While the current power output of prototypes is too low for a modern smartphone's intensive demands, researchers are actively pursuing methods to increase efficiency and integrate multiple smaller cells. According to technology analysts, achieving this would not only free users but also enable radical new phone designs, perhaps even eliminating charging ports entirely, leading to more durable, water-resistant, and aesthetically minimalist devices. Perhaps no application stands to benefit more profoundly than medical implants. Pacemakers, neurostimulators, and other life-critical devices currently rely on batteries with limited lifespans, necessitating invasive surgical procedures for replacement every few years. A nuclear diamond battery could power these implants for the patient's entire life. According to biomedical engineers, this would drastically reduce surgical risks, improve patient quality of life, and lower healthcare costs. It represents a shift from temporary solutions to permanent, integrated biological companions, enhancing longevity and reliability for those who depend on these crucial devices. For deep space probes, nuclear batteries are already a familiar concept, often in the form of radioisotope thermoelectric generators, or RTGs. However, betavoltaic diamond cells offer advantages for specific missions. Their direct energy conversion avoids the heat-to-electricity step, potentially making them more efficient for low-power sensors and longer mission durations. Space agencies and astrodynamics experts envision these batteries powering probes for hundreds, even thousands of years, enabling unprecedented exploration of the outer solar system and beyond. They could keep scientific instruments active on distant celestial bodies for geological timescales, sending back data long after their human creators are gone. Beyond the headline-grabbing applications, nuclear diamond batteries could unlock a host of other transformative possibilities. Remote sensors in extreme environments, from the depths of the ocean to the peaks of inaccessible mountains, or within critical infrastructure like bridges and pipelines, could operate autonomously for decades. Internet of Things, IoT, devices, often constrained by battery life, could become truly fit and forget. According to IoT industry forecasts, millions of sensors could be deployed without ever needing maintenance or replacement. This represents a paradigm shift for distributed intelligence, making persistent monitoring feasible in places previously too costly or difficult to reach. Despite its immense promise, the technology faces significant engineering hurdles to reach commercial viability. A key challenge is increasing the efficiency of beta particle conversion into electrical energy. Current prototypes, while functional, have relatively low efficiencies compared to traditional power sources. Materials scientists are exploring advanced diamond synthesis techniques and dopants to optimize the semiconductor properties, aiming to maximize the number of excited electrons per beta particle. Improving this conversion rate is crucial for generating enough power in a small enough package to satisfy demanding applications like consumer electronics. Another major challenge is scaling up production. Lab-grown diamonds, while increasingly affordable, are still specialized materials. Manufacturing these diamond cells, particularly with precisely integrated carbon-14, requires highly controlled environments and advanced fabrication techniques. Producing these batteries at a scale sufficient to impact global markets presents significant economic and logistical hurdles. According to manufacturing engineers, the cost of synthesizing these specialized diamonds in the isotope incorporation process will need to decrease substantially for widespread adoption, making mass production a long-term goal that requires significant investment and innovation. Beyond the technical challenges, widespread adoption hinges on public perception. The word nuclear often evokes fear and apprehension, even when discussing low-power, contained applications. Overcoming this requires transparent communication and robust public education campaigns to distinguish betavoltaic technology from traditional nuclear power dangers. Social scientists emphasize the importance of clearly explaining the safety mechanisms and the minimal risk profile. Building trust will be crucial for consumer acceptance, necessitating clear, factual information that dispels misconceptions about radiation and radioactive materials, demonstrating that these are not miniature reactors, but precisely engineered energy converters. Where does the technology stand today? Several research groups and startups globally are actively developing betavoltaic diamond batteries. Prototypes exist, successfully demonstrating the principle of converting carbon-14 decay into electricity. These early devices typically generate microwatts to milliwatts of power, enough for low-energy sensors or specialized applications. According to scientific journals, the focus is now on improving power density, increasing conversion efficiency, and refining the manufacturing processes. While still in early development, these tangible results underscore that the concept is moving from theoretical possibility to engineering reality, piece by piece. The introduction of any technology involving radioactive materials requires robust regulatory oversight. National and international bodies, such as the International Atomic Energy Agency, IAEA, and various national nuclear regulators, will play a crucial role in establishing safety standards, licensing procedures, and disposal guidelines for these batteries. This involves careful categorization of the radioactive source and its containment. Legal scholars specializing in nuclear policy predict a complex but necessary process to ensure public safety and environmental protection as this technology matures, requiring new frameworks that acknowledge its unique low-power, long-life profile, distinct from conventional nuclear applications. Persistent myths surrounding anything nuclear often obscure rational discourse. It is vital to address these directly. Unlike a nuclear reactor, which sustains a chain reaction, a betavoltaic battery simply uses the passive decay of a small amount of isotope. There is no risk of meltdown or explosion. Furthermore, the radiation from carbon-14 is weak beta radiation, easily stopped by the diamond casing and a minimal amount of external material. Nuclear safety engineers emphasize that these batteries are inherently safer than many common household chemicals if damaged, with no toxic runoff or combustible components. The hazard profile is significantly different and far lower than public perception might suggest. The long-term vision for nuclear diamond batteries extends beyond individual devices to reshaping our energy infrastructure. Imagine remote communities powered by localized, self-sustaining energy cells, independent of fragile grids. Picture a future where devices are truly permanent, reducing e-waste and our reliance on finite resources. This is not about large-scale grid power generation, but about distributed, enduring micropower. Futurist reports suggest that by providing perpetual power to critical sensors and autonomous systems, these batteries could underpin smarter cities, more resilient infrastructure, and unprecedented longevity for technological endeavors on Earth and in space. The environmental benefits are multifaceted. First, the reduction in nuclear waste. By utilizing carbon-14 from reactor graphite, this technology offers a solution for a problematic waste stream. Second, the elimination of lithium-ion batteries means less mining for rare earth minerals and reduced toxic battery disposal. Experts in environmental science argue that shifting to virtually eternal batteries dramatically lowers the overall resource consumption and pollution associated with our current battery-dependent world. This represents a circular economy approach, where waste is transformed into a valuable, non-polluting resource, offering a genuinely sustainable energy solution. When considering specific applications, nuclear diamond batteries offer an unparalleled advantage in energy density over time. While their instantaneous power output is low, their energy density over their operational lifetime is astronomical compared to conventional batteries. A lithium-ion battery might last a few years, a diamond battery lasts thousands. This means that for applications requiring consistent, low power over extreme durations, the nuclear diamond cell is orders of magnitude more efficient in terms of total energy delivered per unit of mass. Electrical engineers highlight this as the key differentiator for niche but critical long-life applications, where long-term energy storage is paramount. It's important to clarify the difference in power output. Nuclear diamond batteries are not designed to deliver bursts of high power, like starting a car or running a laptop's processor at full speed. Their strength lies in consistent, low-level power. A smartphone's typical power draw is in the range of watts. Current diamond prototypes are in microwatts. This means they are complementary, not direct replacements, for high-drain applications. However, for a device that mostly idles or requires minimal power for continuous operation, this low, constant output is ideal. Battery scientists predict a future where hybrid systems, perhaps a small diamond cell paired with a tiny capacitor for peak demands, might emerge. The idea of using radioisotopes for power isn't new. It dates back to the mid-20th century. Early concepts included atomic batteries using isotopes like polonium-210, but these were often bulky and had short lifespans. More famously, radioisotope thermoelectric generators, RTGs, have powered space missions like Voyager and Cassini since the 1970s, converting heat from decaying plutonium-238 into electricity. Betavoltaics, however, represent a more refined, direct conversion approach, capable of much smaller scales and lower heat output, which makes them suitable for an entirely different class of applications, as energy historians point out. The shift from RTGs to betavoltaics represents a significant evolution in nuclear battery design. RTGs rely on the Seebeck effect, where a temperature difference across a semiconductor junction generates voltage. This heat is produced by highly energetic alpha decay, requiring robust shielding and presenting thermal management challenges. Betavoltaics, conversely, directly convert electron emissions from beta decay into electricity. This bypasses the thermal step, making them cooler, potentially smaller, and more efficient for low-power tasks. As comparative energy studies indicate, this fundamental difference broadens the applicability of nuclear power sources, moving beyond just large space probes. Diamond's exceptional properties are what make it uniquely suitable for this technology. Its wide bandgap means that more energy is required to excite an electron from the valence band to the conduction band, leading to less thermal noise and higher radiation hardness. Its unparalleled thermal conductivity helps dissipate any minimal heat generated. And its extreme hardness provides a robust, physically resilient casing that can withstand harsh environments and potential impacts, crucial for safety and longevity. Materials scientists consider diamond an almost perfect host for containing and converting radioactive isotopes, leveraging its atomic structure for energy generation and protection. While other beta-emitting isotopes like tritium, hydrogen-3, or nickel-63 have been considered for betavoltaic applications, carbon-14 offers distinct advantages. Tritium has a shorter half-life of 12.3 years, limiting device longevity, and is gaseous, making containment more complex. Nickel-63 has a longer half-life than tritium but emits higher energy beta particles, requiring thicker shielding. Carbon-14 strikes a balance, a half-life measured in millennia for extreme longevity, and low-energy beta emissions that are easily self-shielded by the diamond itself. Nuclear engineers confirm that these properties make carbon-14 the optimal choice for the 28,000-year battery concept. The implications of nuclear diamond technology stretch far into the future of energy storage. It challenges the very definition of a battery, moving from a finite consumable to a virtually permanent fixture. This shift could redefine product design cycles, moving away from built-in obsolescence towards devices designed for decades, if not centuries, of use. Energy economists envision new business models focused on initial capital investment rather than recurring battery replacements. This isn't just an incremental improvement, it's a fundamental change in how we conceive, utilize, and manage power in an increasingly interconnected and autonomous world, setting a new benchmark for device longevity. For consumer electronics, the impact would be revolutionary, extending beyond just eliminating charging. Devices could be sealed, making them completely waterproof and dustproof. Freed from the need for bulky battery compartments, industrial designers could create entirely new form factors, perhaps even flexible or transparent electronics powered by ultra-thin diamond films. Technology futurists suggest that embedded sensors in personal devices could become truly invisible, blending seamlessly into our environments, providing continuous data and interaction without ever demanding our attention for power management. It shifts the design focus from battery life to core functionality and longevity. In space exploration, the benefits are even more pronounced. Current space probes are often limited by their power sources, dictating mission length and operational parameters. Nuclear diamond batteries could enable truly eternal probes, allowing them to traverse interstellar space for tens of thousands of years, continuously relaying data. They could power outposts on the Moon or Mars indefinitely, supporting long-term human presence without resupply missions for energy. Astroengineers foresee scientific instruments operating for millennia, observing galactic evolution or planetary changes over scales previously unimaginable, fundamentally altering our understanding of the cosmos. For human health, the transformative potential is immense. Lifelong medical implants were already discussed, but consider advanced prosthetics, brain-computer interfaces, or continuous health monitoring devices that operate without interruption. This ensures consistent therapeutic delivery and data collection, significantly enhancing patient care. Bioengineers envision bionic organs and sophisticated neuroprosthetics that are truly integrated with the human body, powered by a self-sustaining source, removing a critical point of failure in maintenance. It represents a step towards truly permanent, advanced human augmentation, extending both life and quality of life for millions. The current method of dealing with nuclear waste, particularly graphite waste containing carbon-14, involves long-term, expensive, and complex geological storage. Building and maintaining these deep repositories costs billions and requires monitoring for tens of thousands of years. According to government reports, the financial burden of managing this waste is astronomical and falls largely on taxpayers. The nuclear diamond battery offers a potential pathway to significantly offset these costs by transforming a liability into an asset. This economic incentive could accelerate research and development, turning a costly problem into a lucrative solution. Beyond waste disposal savings, the economic incentives for developing nuclear diamond batteries are substantial. The market for long-life, maintenance-free power sources in specialized sectors like aerospace, defense, and medical devices is immense. The potential for licensing and global export of this technology could generate significant revenue. Furthermore, by reducing reliance on volatile supply chains for lithium and other rare earths, nations could achieve greater energy independence. Economic development agencies recognize the strategic importance of such a disruptive technology, potentially creating new industries and high-skilled jobs in its wake, fostering innovation and global competitiveness. The landscape of investment in research and development for nuclear diamond batteries is rapidly evolving. Initially driven by academic curiosity, it is now attracting attention from private venture capital and government grants, recognizing its strategic importance. Startups are emerging, focused on commercializing early prototypes and scaling up manufacturing processes. According to industry reports, collaborative efforts between universities, private companies, and national laboratories are key to accelerating progress, sharing expertise, and pooling resources for expensive R&D. This collaborative ecosystem is crucial for tackling the multifaceted challenges, from materials science to regulatory approvals, necessary for market entry. Given the global nature of nuclear waste and the universal need for advanced energy solutions, international collaboration is proving vital. Researchers from various countries are pooling their knowledge in nuclear physics, materials science, and engineering to overcome the technical barriers. Sharing data, best practices, and even specific isotopes could accelerate the development timeline. Experts in international relations suggest that this technology could become a point of scientific diplomacy, uniting nations in addressing both energy security and environmental concerns. Harmonized regulatory standards across borders would also be essential for global deployment and trade of these innovative batteries. The path from prototype to widespread commercialization is long and arduous, requiring extensive testing and validation. These batteries must undergo rigorous safety assessments, long-term performance evaluations, and environmental impact studies. Accelerated aging tests will simulate thousands of years of decay to confirm predicted lifespans and power degradation curves. Independent verification by third-party organizations will be essential to build public trust and meet stringent regulatory requirements. Engineers underscore that every step, from the integrity of the diamond casing to the stability of the isotope, must be proven beyond doubt before mass deployment can begin. As we look to the future, the nuclear diamond battery represents more than just a power source, it embodies a paradigm shift in our relationship with energy. It's about resilience, autonomy, and sustainability at an unprecedented scale. It offers a vision where energy is not a limited commodity to be constantly replenished, but an integrated, enduring force that quietly powers our world for generations. This technology doesn't just promise to solve battery problems, it promises to fundamentally alter how we design and interact with technology, moving us closer to a truly self-sustaining future, powered by what was once considered unusable waste. This technology forces us to reimagine our fundamental relationship with power. For most of history, power has been intermittent, requiring human intervention, be it gathering wood, drawing water, or plugging in a charger. The 28,000-year battery suggests a future where power is a background constant, seamlessly integrated, effectively invisible. This could liberate human ingenuity, allowing us to focus on higher-order problems rather than the mundane logistics of energy. As technology ethicists observe, such a shift could foster profound changes in human behavior and societal structures, enabling new forms of decentralized, self-sufficient technological ecosystems globally. The journey of the nuclear diamond battery, from recycled nuclear waste to continuous electricity for millennia, is a testament to human innovation. It embodies the audacious goal of not just solving problems, but transforming perceived liabilities into unimaginable assets. While challenges remain in miniaturization, efficiency, and public acceptance, the foundational science and engineering principles have been established. According to leading researchers, the question is no longer if, but when this technology will transition from specialized applications to mainstream use. We are witnessing the dawn of a self-powering future, one shimmering with the enduring promise of diamond. The next phase for nuclear diamond batteries involves moving beyond controlled lab environments into real-world testing scenarios. This includes deploying prototypes in harsh conditions, such as deep-sea sensors, remote Arctic monitoring stations, or even as auxiliary power for existing space assets. These tests will provide invaluable data on long-term performance, durability, and resilience against environmental factors like extreme temperatures, pressure, and radiation. According to project managers, the insights gained from these deployments will be critical for refining the technology, ensuring it can reliably deliver its promised millennia-long power in the varied and demanding environments of future applications. To fully appreciate this technology, consider the sheer quantum leap in longevity it represents. From single-use AA batteries lasting hours, to rechargeable lithium ions lasting years, we are now contemplating power sources for millennia. This isn't an incremental improvement, it's a fundamental shift in scale, akin to moving from sail to steam, or from horses to automobiles. Battery engineers often describe it as moving from finite fuel sources to effectively inexhaustible ones for specific power profiles. This unparalleled duration capability is the core disruptive aspect, promising to fundamentally redefine our expectations for device endurance. While carbon-14 is the primary focus due to its ideal properties and availability from nuclear waste, researchers are also exploring other potential isotopes for future iterations of betavoltaic batteries. Nickel-63, for example, has a half-life of around 100 years, making it suitable for applications requiring century-long power. Strontium-90, though more energetic, could offer higher power densities for certain specialized needs, if safely contained. Materials scientists continuously evaluate the trade-offs between half-life, energy output, shielding requirements, and waste availability, indicating that the carbon-14 diamond cell is just the beginning of a diverse family of nuclear diamond technologies, each suited to different niche applications. Consider the immense power demands of global data centers and cloud computing infrastructure. While nuclear diamond batteries wouldn't power entire server racks, they could provide ultra-reliable, long-term backup power for critical components, or power remote, autonomous data collection nodes. Furthermore, their application in remote sensor networks feeding into cloud systems could enable a distributed, self-sustaining data fabric. IT infrastructure architects envision a future where critical environmental sensors or infrastructure monitors are never unplugged, feeding uninterrupted data for millennia, enhancing the resilience and operational lifespan of our digital backbone without human intervention for power maintenance. As with any powerful technology, ethical considerations are paramount. Questions arise regarding the long-term stewardship of these devices, even if they contain relatively benign isotopes. What happens if a device is lost or disposed of improperly thousands of years from now? While the risks are low, discussions are crucial. Furthermore, the equitable distribution of such advanced power solutions and the avoidance of digital divides are important. Bioethicists, for instance, are debating the implications of lifelong medical implants and human augmentation. These discussions are part of the responsible innovation process, ensuring that the technology benefits humanity broadly and sustainably. The development of nuclear diamond batteries is deeply intertwined with ongoing innovations in material science. Advances in lab-grown diamond synthesis, particularly techniques that allow precise doping and incorporation of isotopes, are crucial. Researchers are also exploring multi-layered diamond structures and heterojunctions to optimize beta particle collection and conversion efficiency. Furthermore, the development of ultra-hard, non-radioactive diamond coatings for additional shielding and structural integrity is vital. Materials engineers are continually pushing the boundaries of what is possible, creating bespoke diamond architectures designed for maximum power output and unparalleled safety, refining the perfect cage for atomic power. The widespread adoption of nuclear diamond batteries could have profound implications for global energy security. By reducing reliance on fossil fuels and unstable supply chains for traditional battery materials, nations could gain greater energy autonomy. For critical infrastructure, decentralized, self-powering components could enhance resilience against cyber attacks or natural disasters that cripple central grids. Geopolitical analysts observe that access to such enduring power could rebalance global power dynamics, fostering localized energy independence rather than reliance on a few energy-rich regions. This is not just about individual devices, but about the strategic distribution of energy at a macro level. The trajectory of many disruptive technologies follows a similar path, from niche, specialized applications to widespread ubiquity. Early betavoltaic diamond batteries will likely target high-value, low-power applications where their longevity and maintenance-free operation are indispensable, such as space probes or medical implants. As efficiency increases and production costs decrease, the technology could then expand into broader consumer markets. Innovation experts predict a gradual but transformative shift, starting with devices where the never-charge feature justifies a higher initial cost, eventually becoming standard as economies of scale are achieved and manufacturing matures, similar to the evolution of solar power or LED lighting. Emerging quantum technologies may also play a supporting role in the future of nuclear diamond batteries. Quantum sensing could be used for ultra-precise measurement of radiation emissions and battery integrity, enhancing safety and performance monitoring. Quantum computing might optimize diamond lattice structures and isotope integration for maximum efficiency. While still speculative, the convergence of these advanced fields could unlock new levels of performance. Physicists theorize that harnessing quantum effects could further refine the conversion process, pushing the boundaries of what these unique power sources can achieve in terms of power output from minimal radioactive material. Even with a 28,000-year lifespan, eventual disposal is a consideration. The radioactive material, carbon-14, will eventually decay to non-radioactive nitrogen-14. However, after thousands of years, the battery will still contain residual radiation, albeit significantly diminished. The design of these batteries includes provisions for secure recovery and recycling of the diamond material, potentially extracting any remaining isotopes or repurposing the synthetic diamonds. Nuclear waste management experts emphasize that planning for disposal from inception ensures that these devices contribute to a circular economy, managing their full life cycle responsibly, minimizing any future environmental burden. Ultimately, the nuclear diamond battery taps into the same fundamental forces that power stars and the cosmos: atomic decay. It's a miniature, controlled harnessing of cosmic energy, scaled down for human utility. This perspective elevates the technology beyond a simple battery. It's a profound connection to the universe's inherent energy. It reminds us that endless power surrounds us, waiting for ingenuity to unlock it. As astrophysicists often reflect, the universe is a vast energy reservoir, and this technology offers a tantalizing glimpse into how humanity might learn to tap into it more sustainably and permanently, leveraging nature's most enduring processes. Despite rigorous safety assurances, achieving widespread public acceptance for any nuclear technology remains a considerable hurdle. This isn't purely rational, it's deeply psychological, tied to decades of fear, disaster narratives, and historical mistrust. Public relations specialists note that information alone isn't enough. Transparency, consistent ethical behavior from developers, and visible endorsement from trusted scientific and regulatory bodies will be crucial. Engaging communities, addressing concerns proactively, and demonstrating real-world benefits in a tangible way will be vital steps to bridge the gap between scientific fact and public sentiment, ensuring social license to operate. The development of nuclear diamond batteries is part of a global race for innovation in energy storage. Nations and corporations understand the strategic advantage of being at the forefront of such a transformative technology. Countries investing heavily in nuclear research and diamond synthesis are positioned to lead this charge. This competition drives rapid progress, but also underscores the importance of international collaboration to avoid redundant efforts and ensure global safety standards. Technology policy experts predict that the winners of this race will shape the future of countless industries, from consumer electronics to space exploration, for centuries to come. One of the unspoken benefits of nuclear diamond batteries is their potential to fundamentally redefine technological obsolescence. In our current consumer culture, devices are often designed with a finite lifespan, compelling constant upgrades. A 28,000-year battery challenges this economic model. It encourages product design focused on ultimate durability, repairability, and upgradability of components around the power source. This could lead to a dramatic reduction in e-waste and a shift towards a more sustainable consumption pattern. Product designers envision heirloom technology, devices built to last not just years, but generations, passed down rather than discarded. Artificial intelligence and machine learning are increasingly being employed to accelerate the development of complex materials and systems like nuclear diamond batteries. AI algorithms can optimize diamond growth parameters, predict isotope integration efficiency, and even design optimal shielding configurations. This computational power drastically reduces the time and resources required for experimental trials. Materials informatics researchers emphasize that AI can sift through vast datasets of material properties and simulation results, identifying novel pathways to higher efficiency and miniaturization that human researchers might overlook. AI is becoming an indispensable tool in bringing this futuristic power source to fruition faster. Despite the long-term economic benefits, the initial economic barriers to entry for nuclear diamond battery technology are significant. The high cost of specialized equipment for diamond synthesis, isotope separation, and precise material integration currently limits production to low volumes. This makes early prototypes expensive, restricting their use to high-value applications. Scaling up without sacrificing quality or safety requires substantial capital investment. Economists specializing in technology adoption highlight that subsidies, government procurement, and strategic partnerships will be crucial to bridge this initial gap and drive down costs through economies of scale, paving the way for broader market penetration. The miniaturization of nuclear diamond batteries hinges on the nanoscale revolution. By precisely controlling materials at the atomic and molecular level, engineers can maximize the interface between the radioactive source and the semiconductor, enhancing energy conversion in incredibly small volumes. Nanotechnology experts are exploring techniques to grow diamond films with embedded carbon-14 at thicknesses measured in nanometers, pushing the boundaries of what's possible for power density in compact devices. This intricate control at the nanoscale is what will ultimately enable these powerful, long-lasting batteries to fit into everyday electronics, opening up possibilities for truly integrated, microscopic power sources. Safety analysis for nuclear diamond batteries includes exhaustive studies of damage scenarios. What if a device is crushed, burned, or immersed in corrosive liquids? Engineers design these batteries with multiple layers of containment and the inherent strength of diamond to minimize the risk of isotope release. The low energy of carbon-14's beta particles means that even if released, their range in air is very limited, and they cannot penetrate skin. Nuclear safety experts conduct simulations and physical tests to ensure that the risk of harm, even under catastrophic failure, is extremely low, far below that of many household chemicals or traditional batteries when damaged. While true perpetual motion is impossible under the laws of physics, the nuclear diamond battery offers something remarkably close from a practical standpoint: devices that run for durations far exceeding human lifespans, effectively requiring no external energy input. This concept of self-sustained operation without charging is profoundly appealing. It allows us to design systems that are truly autonomous, freeing them from the constraints of energy logistics. Energy theorists suggest this pushes the boundaries of engineering, allowing us to approach, if not reach, a state of perpetual functionality for critical devices, transforming our definition of powered. Remote sensing networks are crucial for everything from climate monitoring to infrastructure integrity checks. Currently, these networks often require frequent battery replacements or depend on solar power, which can be unreliable in low light or extreme environments. Nuclear diamond batteries could revolutionize this field by providing truly autonomous, maintenance-free power for decades. This means more consistent data, less human intervention, and the ability to deploy sensors in previously inaccessible locations. Environmental scientists envision vast networks of diamond-powered sensors silently collecting data for centuries, providing an unprecedented longitudinal view of our planet's systems. The advancement of nuclear diamond technology is also an investment in human capital. It requires highly skilled professionals across multiple disciplines: nuclear physicists, materials scientists, electrical engineers, chemical engineers, and regulatory specialists. This drives educational and research programs, fostering a new generation of scientists and engineers. According to academic reports, the challenges inherent in this field attract top talent, creating a vibrant ecosystem of innovation and knowledge creation. This isn't just about a product, it's about pushing the boundaries of scientific understanding and engineering capability, inspiring future generations to tackle grand challenges. Government support, through funding, regulatory frameworks, and strategic initiatives, is pivotal for emerging technologies of this scale. Initial research, often deemed too risky for private capital, frequently relies on public grants. Governments also play a crucial role in managing nuclear waste, which positions them uniquely to support carbon-14 extraction and utilization. Policy analysts highlight that coordinated government efforts can accelerate development, bridge funding gaps, and ensure that safety and ethical considerations are addressed from the outset. This strategic backing transforms promising lab results into tangible national and global assets, ensuring responsible innovation. The nuclear diamond battery isn't a standalone solution, it's part of building a broader sustainable energy ecosystem. It complements renewable energy sources by providing long-term, stable power for critical low-draw applications where intermittency is unacceptable. It also contributes to the circular economy by repurposing waste. Sustainability experts envision a future where diverse energy solutions, from solar and wind to betavoltaic cells, are intelligently integrated, each playing to its strengths. This holistic approach ensures energy security, environmental stewardship, and technological resilience for generations to come, moving away from single-point dependencies towards a robust, diversified energy portfolio. The journey of the nuclear diamond battery is a powerful narrative of scientific imagination transitioning into tangible reality. What began as a theoretical possibility, fueled by fundamental physics and materials science, is now advancing through rigorous engineering and innovative manufacturing. Every segment of this story, from the repurposing of nuclear waste to the promise of lifelong power, underscores humanity's relentless pursuit of better, more sustainable solutions. We stand at the threshold of a new era of energy, where the impossible becomes the inevitable, transforming our devices, our lives, and our planet for millennia. In a world increasingly reliant on portable and ubiquitous power, the nuclear diamond battery offers the ultimate solution: power that is unseen, unfelt, and largely forgotten, simply there. Its strength lies not in explosive bursts, but in its unwavering, silent persistence. This subtle revolution promises to free us from the tyranny of the charge cable, allowing our technology to truly disappear into the fabric of our lives, silently serving us for durations we can barely comprehend. It is the ultimate background power, a quiet, continuous hum that will resonate for tens of thousands of years, powering a future we are only just beginning to envision.